Welcome to the Four Majors, the channel that is dedicated in making science lectures. Anyway, we are going to change the name of this channel into something new. My name is Sir Edgar Angeles, and if you haven't been subscribed to this channel, please click the subscribe button and hit the notification bell to get updated whenever we post new videos like this. So let's dive into it and explore the word of moment of inertia. Let us define the word inertia. According to the dictionary, inertia is a property of matter by which it continues in its existing state of rest or of uniform motion in a straight line unless that state is changed by an external force. So, a body at rest will remain at rest and a body in motion will be in motion or will continue moving unless otherwise it is acted upon by an unbalanced force. Let's try to define inertia in another perspective. Well, we can use another dictionary. Alright, so this is quantity expressing a body's tendency to resist angular acceleration. And the moment of inertia tends to oppose acceleration because from definition, acceleration is the change in one's object's state of motion. Since it is a certain quantity, it can be measured. Alright, let's find the formula for it, Jack. Oh no, Jack, don't run away! In the previous episode, we showed how the force of gravity between two objects behaves in an inverse square relationship, just like the force of gravity that exists between the Earth and the Moon. It is given by the formula F is equivalent to mass times acceleration is equal to K, which is a constant of proportionality, times the mass of the Earth and the mass of the Moon divided by the radius of separation between them. We can actually multiply both sides of the equation r squared by r squared to get, and then we will see that r squared here will be cancelled out and we will arrive at a new formula. And this formula has some implications. Let us now try to identify the implications of the formula. And if you are going to connect these two objects with a rod and they are not balanced at the center, they will rotate, just like what happened in the seesaw. Alright, so if they have the tendency to rotate, they have what you call torque. And torque is involved in this kind of system. We can define torque as the moment of force, or it is also called the moment of force that tends to rotate the system, or it has the tendency to rotate the body to which it is applied. Okay, so the torque specified with regards to the axis of rotation is equal to the magnitude of the component force multiplied by the length of the level arm to which it is applied from a certain distance at a fixed axis. So just like this. Okay, so the wrench is the lever arm and it has a certain length L, and as you can see, there is a force applied that turns the nut in a certain direction. We can now study and explore the free body diagram of this system using this diagram. We can analyze now the forces that are acting on a particle M. And here R is also the radius of this circular path, and R can also be considered the length of the wrench or of the level arm, and the Fr is the radial component, and Ft is the tangential component of the force, and F is the resultant force. Now we can see that Ft here is tangential and is also perpendicular to the radius r. So So this is the situation of the force that is acting uh, on the system, and this force tends to rotate the system. So we are going to multiply Ft, or the magnitude of Ft, by R, and we can get the torque of this system. Since the force that is causing the system to turn in a circular manner is always perpendicular to the radius vector, we can rewrite the formula, and all we have to do now is to rewrite the acceleration from radial to tangential, and it will look like this. Alright, so and you will see that this term from radial acceleration, it became tangential acceleration, and we have a relationship for that, and we are going to show it in the next derivation. And this formula will be equivalent to the torque of the system. And if we are just on the surface of the earth, then this factor will cancel out. All right, so yeah, because there is a certain limit, okay, wherein this thing will be in effect. There is just another way of deriving the formula, and we can do that by making an imagination. All right, so imagine a long rod or a long wrench, just like this. All right, that is allowed to rotate at a certain axis or from a fixed axis, and furthermore, we apply a certain amount of force that is perpendicular to the rod, giving rise to a torque. So we can write this interaction mathematically as torque is equivalent to the product of R, which is the length of the rod, times F. All right, so and that length is where the amount of force F is being applied. We proceed to our derivation of the formula, wherein torque is equivalent to R and times F, wherein we can write F using the Newton's second law of motion, and by putting in mind that the acceleration that we need is the tangential acceleration, because they are perpendicular to one another, as we have shown in the video, and there is a relationship for that. And we rewrite the formula. Torque is equivalent to R times F, and F is equivalent to M, which is the mass of the object, times the tangential acceleration, or the this term is the second law of Newton's second law of motion, and then the tangential acceleration is given by this term, okay, and we have to multiply this to one another, and we will get M, or the mass of the object, times R squared times AZ. All right, and then this term here is the term, the quantity mr squared, is actually called the moment of inertia. We see that from the formula, the amount of torque that is acting on the system depends on where the object is positioned away from a certain distance from the fixed point of rotation. And we can say that there are a lot of objects that are positioned along a certain distance, as what we can see in the diagram. All right, so there may be a collection of objects contributing to the moment of inertia. All right, just like in here. So a certain rod is being hanged or by certain things in different position, and they have different contribution to the torque, and we can sum them up. Okay, we can account for all of their contributions by summing them up. We can now add all the contributions of these individual masses. All right, and we can use the formula for that. and the I is actually equivalent to mass sub 1 times where it is located, and it goes on until forever. And to summarize that, we have this summation notation, and we have to add them all. That's what it means. All right, and the sum is actually the sum of individual moment of inertia contributing to the total inertia. We can also use this in remodeling the formula for the torque. All right. Using the concept of the moment of inertia, and it will be like this. All right, so here we have mr squared times the tangential acceleration. So mr squared is only this term, so we can substitute I for that. So the torque now will have a formula. T is equivalent to R times F, which is later on, using the second law of motion, is equivalent to this. And when we expand the AZ, or get the counterpart of the radial acceleration to the tangential acceleration, we will get this. And when we multiply, we will get this. And then we are going to substitute I for this term. And then this particular formula is called the rotational analog for the Newton's second law of motion. You may wonder if the moment of inertia has something to do with the kinetic energy of the body. We all know that different types of mass are scattered over space. And if the body is moving just like this, they will acquire kinetic energy. We can start our derivation from the main formula for the kinetic energy, which is 1/2 mv squared. But here v is for the linear velocity, and we are going to use the angular velocity. And we have that formula. Don't worry about that. So we can use the concept of the angular velocity. V is equivalent to r times omega, which is the angular velocity. So we are going to substitute it and square that, and we will get k is equivalent to 1/2 mv squared. It's equivalent to 1/2 times the mass times r, and then you have to square that, and then you have to square this, and we will see that the sum arise again, and we can rewrite it as I for the moment of inertia. Okay, and therefore we have k is equivalent to 1/2 I omega squared as the formula for the kinetic energy due to the rotational motion of rigid objects. So do not be confused with the word moment as in the moment of inertia. The word moment there means that the moment of inertia I depends on the distribution of mass in space, and it has nothing to do with the other meaning of the word moment, as in moment in time. So the moment of inertia of a certain object is due to its mass distribution. Now, how can we calculate for the moment of inertia of the Earth, knowing that it is not made of only one kind of material? To solve this problem, we need to apply the formula that we have devised earlier, which is this. Okay, so this formula is very useful, and we can actually get a sample of materials coming from the Earth, and then we arrange them into a long cylindrical rods, and then add these rods together so that we can fill the entire volume of the Earth, and then we can get the moment of inertia of the entire planet. And we remind ourselves that each sample material have their own density. So moment of inertia is a combined factor of the object's geometry and mass distribution, just like a solid cylinder. The moment of inertia of a solid cylinder is different from that of a hollow cylinder because the this portion of the hollow cylinder has no mass. Alright, so it's empty. So therefore, you can expect that there is a difference in their moment of inertia. Moment of inertia also depends upon the axis of rotation or where the axis of rotation is placed. A slender rod may have different moment of inertia if they are made to rotate at different axes. We have some more objects like the circular disc, okay, whose figure is shown right here. And we also have a solid sphere just like the Earth. And we know that it has three axes, namely the X, the Y, and the Z. Now that we have prepared ourselves to undertake the calculation for the momentum of the Earth, alright, so yeah, here is our planet Earth, and there we go. We have core, we have the outer core, we have the inner core, we have the mantle, and we have the crust. Okay, so we can try to calculate the moment of inertia of our planet. So we can assume that it is a perfect sphere or a solid sphere in shape, and we can calculate for its volume using the formula V is equivalent to 4/3 pi r cubed. And we can relate the formula of the volume to density using the formula that we have here. The density is equivalent to mass over the entire volume. Alright, so because we need to do that, we need to find the average density of the Earth. Alright, because the Earth is made of different layers and made of different materials. So we just have to find a density function that can model the density of the Earth, and then we are going to substitute it to our formula. And let's see if we can devise another way wherein we will not use the density of the Earth. Let's see if we can do that, because there is a lot of issues in using the density of the Earth and making the moment of inertia calculations. But in reality, it is real that the Earth is made out of different layers, and they have different density. So following the relationship that we just laid, we know that the mass is distributed differently, so we can say that the density is a function of the change in the mass per unit change in volume. So we are going to use a little bit of differential equation or differential calculus. Alright, and then we can solve for dm, because that is the change in volume, and dm is related to the moment of inertia. Alright, and then we can write dm, or the change in mass, is equivalent to the density times the change in volume. Alright, and then we have to integrate on the entire volume to get the total moment contribution of dm. So the total moment of inertia, we can rewrite the integration formula as this one. Alright, so this is just also the formula for the moment of inertia. It just look a little bit different, wherein dm is the infinitesimal contribution of mass, okay, and then r squared is the radius, and in our case that would be the radius of the Earth. And then we are going to substitute our formula for dm, which is pdv, and we can rewrite it as I, or the moment of inertia, is equivalent to the integrand of r squared times the density times dv. Or yeah, so because we assume that the density is constant, so we can rewrite it outside the integrand, and we just need a factor that enables us to integrate over the entire volume. Okay. So the Earth has three spatial dimensions or spatial dimensions, so we have to decide on how we can carry out the integration process. And the best way to do this is to cut the Earth into thin circular discs. So I'm gonna give you the pattern in our problem solving. So this is how we are going to solve the problem for the moment of inertia of our planet, but this also applies to the moment of inertia of any object of a certain geometry. Alright, so for the Earth, alright, it is a solid sphere, so just like this, and it has three axes, namely the X, Y, and the Z axis, and this one will be our C axis, and this is our thin circular disc. Okay, imagine that we cut the Earth into several pieces, 1,000 pieces of this thin circular disc, okay, whose volume is equivalent to dV, and that is equivalent to pi x squared dz. Alright, and this x-axis is just an arbitrary axis, alright, because this one is the radius coming from the center of the x-axis going towards here. So dm is equivalent to pdb. Alright, so we are going to substitute pi x squared dc into this formula. Okay, so and by the way, the moment of inertia of a thin circular disc is di is equivalent to 1/2 dm, okay, x squared, so that it is equivalent to 1/2 times the density times this one, which is the dv. Okay, so this is pdv times x squared. I, or the moment of inertia of the thin circular disc, is equivalent to 1/2 r squared m, and we just have to put the formula for m or for dm, and then we are going to arrive at the answer, or we will carry out the integration process. But first, take note that the distance from the equator gets larger, the radius of the outer thin cylindrical disc gets smaller. So there is a change in dr in the radius along the z-axis. Alright, so what we're gonna do is to find a trigonometric substitution for this, and then carry out the integration process. So we can use the simple trigonometric substitution for this to find dr, and given the z-axis and the radius distance from the center of the Earth to be r squared minus c squared. Alright, so that is equivalent to this formula. Okay, and then we will get this one. So because we substitute r for r squared, and then r for r squared, and then dm, so m and dm would be changed. Alright, so we have a formula for dm, which is pdv. Alright, so this one, the formula will look like this, and then we are going to put p, or the density, outside, and then we get dv of the thin circular disc. Alright, and then so the area times height is the volume, which is pi r squared dz. Alright, so the formula will look like this, and then put all the constants outside, All right. And r squared times this one is r to the fourth power. All right. Then we have to integrate from negative z to positive c, or from negative r to positive r. Okay, so it seems easy to integrate this, but remember that there is a change in dr as um, we go away from the equator, and we have to account for that change. So this is an incomplete formula because we have to account for that. Okay. So the right formula would be this one. So r squared minus z squared is the right formula for this term. Okay. So we expand the polynomial. Okay, we will get r to the 4 minus 2r squared z squared plus z to the 4, and then we are going to integrate with respect to the z-axis, so we will get this formula. Okay, r to the 4 times z minus 2zr squared c to the power of 3 over 3. So this is the rule in integration. Okay, so you can review your lessons about the integration process. Alright, and then alright, so we will change now the variable from z to r. Alright, so we'll substitute r for z, and we will get this thing. And then once we solve this, r to the 5 times 15 over 15. So because we have to create and join this term to all together using the common denominator, and once we do that, we will get 8 over 15. Alright, so y2, because of the rules in integration. Okay, you can try to explore that. So you have 1/2 density times pi times 2r to the 5th power times this one, and then the sum of this one is 8 over 15. Alright, and we can simplify this using the formula for volume. Okay, so substituting the formula for density, since we do not want to use the density calculations of the earth because there is an anomaly for that because of the mass distribution, as I've told you. So we have to do is this one, and then m over 4 pi r cube is the volume of the earth. So we will cancel out several terms. R, so r to the 5 divided by r to the 3 would be r squared, and then this one will be cancelled out, and I'm gonna show you that. 1/2 times 2 over 1 times 8 over 15 times 3m over 4 pi r to the power of 3 times pi r to the power of 5, and then the solution is 2 over 5 m r squared, wherein m here is the mass of the earth. As I've told you, the density, as if we are going to use the density of the earth, we will be misled because the earth is not uniformly whose mass is not uniformly distributed all throughout. Okay, so the moment of inertia of the earth is therefore 2 over 5 times the mass of the earth r squared. And then We can calculate now the moment of inertia of the Earth by substituting the values like this. And you can press this in your calculator. That's all. And once again, my name is Sir Edgar Angeles, and this is the 4 majors. And if you haven't been subscribed yet, please click the subscribe button and hit the notification bell to get updated once we post new videos like this. And please also give us a like if you like our content. And I'm leaving you a message: knowledge will be your power. Bye bye.